In this lesson, we're going to go over exponential modeling. So first we'll review exponential growth and decay, and then we'll understand and calculate application problems about exponential growth and decay that can really be modeled with an exponential function. So as a quick review, we've talked about exponential growth and decay as a trend that makes a quickly changing curve, and it occurs when a quantity grows or decays by the same percentage in each unit of time. We've talked about exponential growth with doubling time and also with half-life, but in this lesson we are going to talk about it with different rates or percentages of growth or decay that were given. And so for the exponential function, this is the general form. Q is equal to Q naught times 1 plus r raised to the t power, where Q is the quantity after time t. Q naught is the initial value of the quantity, and it needs to correspond to t equals 0. So that's when you start counting or when you start measuring. R is the growth rate as a decimal. Note, that should say note, not. R is negative for decay. Okay, so if something is decreasing, make sure that R is negative, and then T is in time. And just another note that the time units for T and R should be the same. And so if your growth rate is in days, your time should be measured in days. Or if your growth rate is in years, your time should be measured in years. If those don't match, you have to make a match. Okay, so example 1, the average home price in Las Vegas trends up at a rate of 12.5% per year. The average home price in Las Vegas in 2012 was $100,025, $25, and $317. So create an exponential function to model this situation. So in this case, we're going to use our starting value of t equals 0 as 2012. Our rate is 12.5%, which as a decimal is 0.125. It's trending up, it's growing, so it's going to be positive. And then our starting amount is $125,317. Okay, so we can write our function as Q is equal to $1,225,317, 1 plus 0.125 raised to the t power. And then I would just advise do the addition, or if it's a decrease, do the subtraction there. So Q would equal notice this portion, at least the 1 plus the rate, looks a lot like the markup formula. That's what's happening is it's, whatever was there originally, it's growing a certain percentage on top of that. Okay. So complete the table showing Q for the first 5 years, round all answers to the nearest dollar. And so what you would do here is our starting value corresponds to t equals 0, which is 2012, so that part has already been filled in. So for 2013, time is 1, 2014 is 2, 3, 4, 5, and so on. Okay. So then what you would do is you would plug this into the formula where Q naught, 1 plus R would stay the same, and then each time you're using a different value of T. So I'll write out the values here and make sure that you get the same thing in your notes. And again, that's rounding to the nearest dollar each time. If you were asked to graph the function or determine a graph of the function, line up your values. So our starting value was a bit over 100,000, okay, and then as it trends upward, but it is going to make a rapidly changing curve. And then continuing on, use the graph to predict the home price when t is equal to 10, and then what year corresponds to t equals 10. And so if we look on our graph, t is equal to 10, so we're going here. This looks like it's about $400,000. And then t equals 10 is 10 years from 2012. And so when you add that on, we would end up at year 2022. Okay, so that's just to remind you that all of this is in reference to a certain starting point in time. Example number 2, a car's value depreciates by 20% each year. The car was originally purchased for $15,000. Create an exponential function to model the situation. This may sound familiar. When we first started talking about exponential growth and decay, I used this example and we calculated it by hand each time. but now you have the opportunity to see it as a function. So I would encourage you to go back to that example if you'd like to see the connection between writing out what happens each year when it depreciates versus using the function. So our starting value is 15,000, and that's going to correspond to when you first bought the car, or t equals 0. Our rate in this case is 20% decrease, so it's going to be negative 0.2. So here we have Q is equal to 15,000 times 1 minus 0.2 raised to the t power. So this is 15,000 times 0.8 raised to the t power. And again, we talked about using percent increase and decrease or markup and discount. Notice that if a car loses 20% of its value, it's retaining 80% of its value. So that's where that 0.8 is coming from in the formula. Okay, so use the function to determine how much the car will be worth in 5 years. So 5 years corresponds to t equal 5 because we started at year 0. And so we'd have Q is equal to 15,000 times 0.8 raised to the 5th power. And this comes out to be $4,915.20. Same thing we got when we calculated it 1 year at a time, determining the value. Thank you for watching. If you have any additional questions, please feel free to reach out to me.